Hello! So far we have learned quite a bit about one-dimensional motion. Kudos! Now, in this lecture, our job would be to learn how to analyze different kinds of motion. We have solved problems involving motion variables or kinematic variables, and now we want to analyze motion and see how that helps us. Okay? So we choose to study two common ways which are used to analyze motion. One of them is motion diagrams. So what is a motion diagram? Well, motion diagram you can think of as snapshots of an object moving in time and position. And so what this does is qualitatively analyzes that object's motion. How? Well, you can look at the snapshot at different times, and and based on the position of that object, we can say, or we can analyze that motion qualitatively, whether it was moving, whether it was at rest, whether it was accelerating, and so on and so forth. So let's look at an example. Here, let's consider time is this way, moving forward, and position is starting from 0 and moving forward to the right. If we have an object which starts at 0 and then moves like this, look at the object's separations in time, we can say that the object is accelerating in time, right? Because the position change with time is not equal. So this is the motion in its first second, this is the motion in its second second, this is the motion in its third second. So every second the change in position is not uniform with the first second. Okay, so this is an example of an accelerating motion. If you look at another example, we can see that the position of the object is uniform in time. So for example, in 1 second the object moved 1 meter. From 1 to 2 seconds the object moved another 1 meter. From 2 to 3 another 1 meter, and so on and so forth. So the position change is uniform in time, and we can say this is motion for a constant velocity. Okay, and if by looking at these diagrams we can see that we are qualitatively analyzing its motion. We are just saying whether an object is accelerating or moving at a constant speed or not doing anything. We are not mathematically defining any kinematic variables in this kind of analysis. That's why it is a qualitative analysis. But in physics, a more important analysis would be a quantitative one, and motion graphs gives us that option. So what does that do? Motion graphs traces out one kinematic variable against another, just like you would do in normal math problems with x and y axis. So on x axis you have one kinematic variable, which is, we say, the independent variable, and with respect to that, on the y axis we choose another motion variable, for example, say position. So this motion could be traced out using a motion graph to give it a more quantitative picture. So what motion graphs does is allow us to analyze the motion in question at a more deeper mathematical level. We are going to study three types of motion graphs. Position time graphs. So the independent variable is in the horizontal axis and the dependent variable is in the vertical axis. So usually time is always the independent variable, so always on the horizontal axis, while we want to see how position changes in time. So position is dependent on time, hence on the vertical axis. Similar to that, we have velocity time graphs, and we denote position time graphs by xt. We denote velocity time graphs by vt graphs, and also we have acceleration time graphs denoted by at. The important thing to realize, and we will see examples of it, is that all of these three are connected to each other. So from a position time graph, you can trace out the velocity time graph. From an acceleration time graph, you can trace out a velocity time graph, and it goes back and forth as well. From velocity you can go to acceleration. So let's look at an example. So we have position time graph set up here. So we have position x on the y-axis and time t on the x-axis. So with the naming, it is pretty easy to remember that whatever comes before is on the y-axis, so x is named before t, so x comes on the y-axis and t comes on the x-axis. Okay, so we have two objects, say two people moving. Okay, so we denote the purple curve by 1, so person 1, and we denote the blue line or blue graph by 2, so the second person. Okay, so they start at the same time because they both start at 0 seconds, and then their motion is traced out as follows. Okay, so we can see they are very different kind of motions, but we can compare even these sorts of different motions using principles from motion graphs. How? Well, a very important property of motion graphs is slope or gradient of the graph. So to learn more about analyzing motion from the graphs, first we have to talk about some properties of every graph. So the first thing that should come to your mind when you see a graph is the slope of the graph. Okay, so what is a slope? A slope is the steepness of the line you take to go from one point to another point. For example, let's say we have a coordinate system, x-axis, y-axis, and this x is not position for this current example, and you have 2 points that you move on. Say you move from point A, that is here, and point A has x coordinate xa and y coordinate ya. So we write coordinates as parentheses xa, so the x coordinate comes first, y coordinate comes second, and you move on to a point B with x coordinate xb and y coordinate yb. Okay, you connect the 2 points to make a straight line. Forgive my bad lines. And you make a right angle triangle out of it. This is my slope or steepness, or also called gradient of that particular line. How do we find that? Slope or gradient is equal to the y coordinate of the second point, which is yb, minus the y coordinate of the first point, ya, over the x coordinate of the second point, xb, minus the x coordinate of the first point, xa. So this will give you the gradient or slope of that particular straight line. Okay, now in the context of position time graphs, what is a slope? What is the slope for a position time graph? So in physics, unlike in math, our equations must have a physical meaning. So if you just write down the slope of this, say person 2 is so and so, you give a number using this formula, it doesn't give you a complete picture physically. So the motion graph, the slope of a motion graph must represent something physical. So what does this represent? So if you say take the graph of the person 2, okay? So this is person 2. It is basically just a straight line. The point that I want you to know is that, or want you to understand, is that the slope of a straight line is constant throughout, meaning the slope of this triangle is the same as the slope of this bigger triangle is the same as the slope of the biggest triangle, because it is a straight line, and straight line means constant slope throughout. So to calculate your slope of the person 2, you can use any 2 points on the straight line. I choose to use the origin here, the beginning of the journey, where time was 0 seconds, which is the x coordinate, and the position was also 0 seconds here, okay, because the journey didn't begin as of yet. and then I choose any other point. Maybe I choose this last point or something, okay, and say this last point of this point of the journey has y coordinate 8 and x coordinate say 6, doesn't matter. So 6 and 8 is my final point. Okay, now the gradient is equal to, using that formula, yb, this is my b, this is my a, yb is 8, the second coordinate, and ya is 0, over xb is 6 minus xa is 0, and this is 1.5, right? Now the y-axis represented something physical in this graph. Y-axis was position. Position has units of meters. So up here you had units of meter. X-axis represented something physical, the time, having units of seconds. So you have seconds as the denominator. What is the unit of the slope then? It is meters over seconds. What does this unit represent? Nothing but velocity or speed. Okay, now that means slope of xt graph gives velocity. Very important to know. Now that we want to investigate a region or the time for which the two people moving on represented by these two graphs have same or similar speeds, okay, or similar velocities. How do we do that? We have just found the velocity for person 2, which was constant throughout, okay, because velocity is the slope of the graph, and the graph for person 2 is a straight line which has constant slope, and hence we can say it has constant velocity. So it was constant throughout, and we want to say where on this curve for person 1 was the velocity at 1.5 meters or near about, okay, because this is not to scale. So we ask, hey, how do we calculate gradient for a curve? We just saw how to calculate gradient for a straight line. You're correct. So let's see how we can do that for curves now. So for curves, we need to draw things called tangents. What does tangents mean? Tangents are basically straight lines through a point which will graze the point but will not cross the curve. Okay, for example, we can investigate the tangent at many points of this purple curve. So we have 3 points, so we can draw straight lines through those points like so. Okay, see how they grazed that point but didn't intersect or didn't cross the curve. Similarly, we can do this for this point, touching the point but not crossing the curve, and so on and so forth. We see that from the beginning of the motion, the curve is flattening out because the slopes of these tangents are flattening out. So at each of these points, we can see that straight lines are different sloped. So the slope is changing over time. Hence, the slope at any two different points will be different for this curve. Okay? We want to investigate the slope or of a point which looks kind of similar to this straight line. So we look at a tangent which is sort of parallel, close to being parallel to person 2, because parallel lines have the same slope. Okay? So we see that this tangent here is parallel or looks parallel to person 2. So let's say this time is 2 seconds, okay, and the position for this curve in 2 seconds was, let's say what I have down here, around 5.1, okay, So our goal is to use any other point on this tangent to find the slope for this tangent line. Okay, so I choose a point which has time 2.8. You could have chosen any other point, but because this is not to scale, I have just forced my hand here and made it 2.8, and the corresponding position to 2.8 I have chosen to be 6.4, I believe. Okay, now we can calculate the slope for these 2 points on the same tangent line. So they will have the same slope. This point right here will have the same slope as this point and this point, and so on, as long as it's on the same tangent line. So we have established our 2 points. First point is 2, 5.1, and notice that the x coordinate always comes first, the y coordinate always comes the second, and 2.8 and 6.4. So we want to find this slope. So slope for this particular triangle is YB is 6.4 minus YA is 5.1 over XB is 2.8 minus XA is 2. This comes out to be, and remember the units are meters over second, like so, 1.6 meters per second. So this is similar, very close to 1.5 meters per second. So we can say that 1 and 2 had similar velocities at t equals 2 seconds, or somewhere in between t equals 2 and 3 seconds. Okay, so we have already learned that position time graph is related to velocity time graph in that one can be derived from the other. Let's see how, or can we actually do that? Can we actually derive the velocity time graph for the position time graph that we just studied? Okay, all right. So few important things to note about this motion graph is that we have 2 objects moving or 2 people moving, and we have 2 different graphs, right? One for person 1 in purple and one for person 2 in blue. Now we see that we already noted that the velocity of person 2 is the same throughout. Why? Because it is a straight line. The slope of a straight line is always constant, and on a position time graph, that just means the velocity, which is equal to the slope of the graph, is always equal. Okay, always the same. So if you want to derive velocity time graph from position time graph, we have to know that for person 2, the velocity time graph would be velocity time would be a horizontal line like this at 1.5. This is meters per second, this is seconds, at 1.5 meters per second. Why? Because this y-axis velocity is actually the slope of the position time graph. So this value is the slope of that particular graph, which is always constant at 1.5 meters per second. So this is the velocity time graph for person 2. For person 1, it's a bit different, right? So for person 1, we have seen that for any curve, the tangents at each point in time is always changing. For this particular curve, we have seen that the tangent the tangents at each of these points started out pretty steep, but started flattening out. Flattening out of tangents means that the slope of the curve was decreasing as time went on. Slope decreasing means that you have a decreasing velocity. So you started very steep slope, that means you started at a very high velocity, person 1 did actually, and then as time went on, the velocity of person 1 started decreasing. The graph for person 1 then just means that you start at a high velocity, call it v2, and the velocity keeps decreasing over time until the velocity of person 2 goes to 0, because at the end of the motion, denoted by this graph, the tangent at the last point has flattened out. A flattened line, a horizontal line, just means the slope of that horizontal line is 0. So that means the velocity at the end point is 0. So this is how we can derive the corresponding velocity time graph from the given position time graphs. Now that we have the velocity time graph from the given position time graph, we can investigate some properties of this velocity time graph. First, let us investigate the slope of velocity time graphs. So for a horizontal line, the slope is 0. And because if you use the formula that we talked about, yb minus ya over xb minus xa, you will see that the y coordinate is not changing. So yb here minus ya here would give you a 0. So ultimately the slope would be 0. For any other sort of straight line, the slope is non-zero. So this is a non-zero slope, and again we also learned that slope for a straight line is constant throughout. So at any 2 points on this straight line, the slope is the same value. So let's calculate the slope for this purple graph, the graph for person 1. Let's say he or she started with a velocity of 6 meters per second and then went to 0. Okay, and so we have 2 points. The starting point A right here is with x coordinate 0 because it starts from the origin, which just means that at origin time equals 0 and velocity equals 0 for this particular axis. So x-axis is 0, y-axis is just 6. Here we have the finishing point B, x-axis is 8, y-axis is 0. So the slope would be yb minus ya, yb is 0, 0, minus ya is 6, over xb is 8, minus xa is 0. And the units would be, in the y-axis we have units of meters per second, and on the x-axis we have units of second. So we end up with minus 0 minus 6 is a minus 6 over 8, and the units become meters per second squared. The most important thing to realize, first of all, meters per second, what does that represent? Acceleration. So the slope for VT graph gives you acceleration. Second thing to notice is this negative sign. As we have learned that negative acceleration can mean 2 things, either a negative speeding up, which is a negative acceleration per se, or a deceleration, which means you are actually slowing down. Here we see that the person 1 started with high velocity of 6 meters per second. At the end of its motion, it became 0 meters per second. So the velocity went from 6 to 0, hence slowed down. This means deceleration. Okay, so we see a graph sloped like this, starting at high, finishing at low, would be a negative sloped graph, because we are actually denoting vectors in these graphs. Another important property of velocity time graph is area under VT graph. Why? Let's see. This one was person 2, 1.5. And this one was person 1, starting from high velocity V2 and ending here. All right. Now, let's say we want to calculate the area under the velocity time graph. So let's just say both finishes their journey at 8 seconds. Okay. So first of all, let's work with person 2. So we can see that the person 2 area would be this, which is geometrically a rectangle. So area of a rectangle is area under this person 2's graph. It's just a rectangle, which is length times width. Okay. The length is 8 seconds times the width is 1.5 meters per second. Seconds go away and you end up with some number 8 times 1.5 meters. So what does that tell us? That just tells us meters. What does meters represent? It represents any length, right? Or displacement or distance. Since it's a velocity time graph, the area under velocity time graph represents the displacement. Okay? Area under VT graph. Having been given a position time graph, from that we derived velocity time graph. But we also said we can also derive an acceleration time graph. So how would that look like for this motion? So here we have again the axis. On the y-axis we have A. On the x-axis or horizontal axis we have t. So we can see that we have two people. So person 1 has zero slope. Zero slope means zero acceleration. So this is actually person 1 for whom acceleration is 0. So it's just along the time axis. Okay. But for person 2, we just found out that the acceleration was negative 8 over 6 meters per second squared. Correct? So we have to go into the negative axis, and this would be, so let's we would go to the negative axis, and this would represent 8.2 equals negative 8 over 6 meters per second squared. Okay. So this is how we go from position time graph to velocity time graph to acceleration time graph. And for our purposes, we don't need to know much of the properties for acceleration time graphs apart from just deriving it from given velocity time graphs.